Hello students, considering the situation we are going on, I have decided to make some videos for you. Okay, so today we will be discussing about error committed in trapezoidal rule. Okay, we have already derived the trapezoidal rule, but now we will be seeing what is the error incorporated in that rule. Okay, so for that my starting point will be my quadrature formula. I have already derived this equation in the class. So if you are unable to understand, then you let me know, I will make a video of it. Okay. So if I close this. So basically we are doing the integration, okay? Integration of from a to b fx dx. That is basically, if I see this graph, this is a and this is your b, and this is my arbitrary function. So I have given an example in the class. Consider this one as the roof of your college, RCCIIT. Then this is your this is one side of the wall, this is another side of the wall. I am trying to find the area of your college. That is basically I want to do the integration. Fine. So now this is the quadrature formula, right? So I told you, if I put this n, what is n? N is basically the number of intervals here. Number of intervals. So if I for this case, for this figure, there is only one interval. That means one chunk of area is present here. If I divide this function, this area, into number of sections, then my n will give the number of sub intervals. Okay. So for trapezoidal case, my n should be 1. That means I will take only one chunk of an area. Okay, so if n equal to 1, that means this figure basically this figure. So how many points are there? There are 2 points, a and b. So this is my first point I have discussed. This is x0 and this will be my last point. Since here we have 2 values, so this is basically x1. Okay, so this is x0. If I have shifted to that side, that means basically x1. That is basically x0 plus h. This distance will be h. This gap is basically h. Okay. So this y0 is basically the function value at x is equal to x0. That is basically our fm, this point. And y1, that is basically function value at x1. Now what is x1? x1 is this point. That is basically f x0 plus h, x0 plus h, and then this is basically the last point. So for this case I am telling, for this case, this is my fb. Okay. So until this point, I hope it is clear. Now put n equal to 1 here in this equation. What will happen? Put n equal to 1 in this equation. What will happen? Now see, that is hy0 plus this will be 1 square by 2. It is basically del y0 by 2. Okay, and where are the other points? Where are the other terms? The other terms, this is basically del square y0, right? This is del square y0. What is del square y0? It is basically, if you can recall from the difference table, this is basically the difference of del y0. So for this case, what is del y0? Del y0 is simply the function value differences, y1 minus y0. So for this case, I have only one del y0. So how can I find del square y0? Because for del square y0, I need two delta values. But here, since we are considering only 2 points, so there will be one del y0. Fine. So for that case, so del square y0 and the other terms will be basically 0. So my ultimate term will be IT. This is T for trapezoidal case, and this is H y0 plus del y0 by 2. Only this much. The other terms will be neglected. Okay, not neglected, the other terms will be 0. Okay, now let me put back this phone. Now see, so basically IT is IT is y del 0, y0 plus del y0 by 2. So now del y0 can be written as y1 minus y0. Fine. Then what will happen? Just put y1 minus y0 in this equation. So I will get this one. Right? Now, if you simplify this one, I will get h by 2 y0 plus y1. Only this much I will get. Fine. Now, what is basically y0? This is basically fx0. So I can write instead of y0 fx0. And what is this fx? What is this y1? Y1 is basically fx1. That is basically fx plus h. So fx plus x0 plus h. Okay. So I hope this line should be clear. Now I can't play with this one. This term. I can't play with this. Let me make it closer for you. So, but I can play with this one, this term fx0 plus h. Fx0 plus h. What is fx0 plus h? If you can apply Taylor's theorem here, so what will happen? It will give, the first term will be fx0, this will be fx0, h by 2 will be already there. Now fx0 plus h, I can write it as fx0 plus h plus, fx0 plus h into fx0 plus h square by 2 factorial f second derivative of x0, and likewise this is from Taylor's theorem, you know. I hope you know that. So what I have done here, just simply expanded this fx0 plus h. Okay, this is basically fx0 plus h fx0 plus the other terms. Fine. So keep it. Let's complete this part. Okay, leave it here. Just leave it here. Okay. Now see what? How can we find the error here? So this is my error term. What is this error? Error term will be T for again trapezoid. So my total, the integration of functions, that is a to b fx dx minus, we have approximated this it, right? Approximated this it, and we have found that it is basically this one, the last term, the last equation. So error is basically my actual value minus this expression which I have derived just before. Okay, so this part I have kept as it is, and this one it can be written from the other equation is this much, that is basically h by 2 fx0 plus fx1. If you can just pause the video or just rewind the video, and we will see this is it is basically h by 2 fx0 plus fx. Okay. Now we have already found out this part. This it we have already found out. That total expression just before I did. Now this one a to b fx dx, we are considering fx to be a finite continuous function which possesses continuous derivatives, okay, of all orders. Why of all orders? If I expanded it, I will get for the first term normal fx, then I will get f dash x, then f double dash x, then f triple dash x, like that way. Okay, so I need all the derivatives of all orders. Fine. So you can write it possesses continuous derivatives of all orders. Fine. Now since this fx possesses a continuous derivative, so I can write fx as f dash x, this capital F dash x, I have chosen a function, this one. Since fx is basically equal to capital F dash x, we are considering an fx, capital Fx, such that this fx, this small fx is equal to the first derivative of capital Fx. Fine. Now just integrate this both sides. Integration from where to where? We have only 2 points, that is basically x0 and x1. So x1 is x0 plus h, so integrate from x0 to x0 plus h, fx dx, and then if you integrate this one, this is f dash x, right? So if you integrate it, what will get? We will get f dash x, sorry, fx. So fx, and if you put the limit, so fx0 plus h, and this is fx. So this one is basically, this one is, if I integrate f dash x dx, what I will get? I will get capital Fx, right? And my integration limit is x0 plus h. So one term will be fx plus h minus fx. Fine. Okay. Fine. Now fx0, keep it as it is. Now this capital Fx, capital F x0 plus h, similarly I can expand. In the earlier case we have small f x0 plus h, here capital F x0 plus h. Fine. So now expand this one. Just expand this one again by Taylor's theorem. Okay, so first term will be fx0, then will be h, f first derivative at the point x0, then x square by 2 factorial f double dash x0 like this. Okay, and there will be, remember, this minus fx0 is there, so write minus fx0. Fine. Now see this first term and this last term, there we can cancel out this one. This is plus, this is minus, so you can cancel out this. So the other terms you will write. Other terms, I have written all the other terms. Fine. So can you see? Fine. Now see. So this is basically what we got. H capital F dash x0 plus h square by 2 factorial if double dash x0 plus h cube by basically 3 factorial, that is 6 f triple dash x0 likewise. Fine. Now what is this f dash x0? What is this f dash x0? See here. This, if I replace x by x0, then f dash x0 is basically f small f x0. So my first derivative is basically my function at x0. So I can write h fx0, this one, this f capital F dash x0 I have replaced by fx0. You can map with this one. And what will be my next term? H square by 2 factorial f double dash x0. Now f double dash x0 can be written as small f dash x0. Why small fx? See, if capital F dash x0 is f x0, what will be my f double dash x0? It will be f dash x0, f dash x0. So basically one order of derivative is decreasing here. Fine. See, the 3 becomes 2, then 4 will become 3, like that. Fine. So keep it as it is. Now what I need to do, this part is all what I have derived is basically this part, only this part. Fine. This is already we have derived last time. Now just subtract this 2 from this equation. That is, from this equation subtract this equation. What will you get? All will cancel out. only this third term, the third term, h cube, this term, h cube, f double dash x 0 by 3 factorial, this is basically 6, this one, and for this case it is h cube, this one is basically h square by 2 factorial, this one, this, okay. So just subtract this two, and remember there is h by 2 here, so h by 2, so 2 will become 4 here, and then the other terms, that is there is a 4, 5, 6, 7, we have just neglected. We have taken only this second derivative of small fx at x0. The other terms I have just neglected. High power terms neglected. So this ET, basically the error incorporated in trapezoidal rule. Okay. So this much for today. Now there is another rule, just I am discussing composite trapezoidal rule. Composite trapezoidal rule means, see here there is only one interval, right? So if I have break that area into suppose n number of sections, then what I can do, I can find out each area through this trapezoidal rule. Each means from 2 points, taking 2 points at a time, I can find the area, fine. So if I proceed that way, I will get the composite trapezoidal rule which I have discussed in the class, that is the total equation, h by 2 plus y0 plus yn plus 2 into rest of the terms, fine. So that is a composite rule, and for that case the error will be just simply this, for this simply like this, one n will be just incorporated here, only one n will be incorporated here. This is h and there will be one n, so nh cube by 12 f double dash x 0, fine. So this is for composite trapezoidal rule. Okay, thank you.